At the heart of machine learning, we constantly face a challenge, making sense of incomplete data. I'm not talking about data with empty cells, but information that is, so to speak, hidden. Imagine we want to understand the preference of a store customers, but we only see what they buy, not the underlying reason for their purchase. That reason is a latent variable, a shadow that influences what we observe. How can we build an accurate model when a crucial part of the story is hidden? The answer is an elegant and powerful algorithm, expectation maximization, or simply EM.
Let's take a tangible example. In air traffic control, a radar sends a signal and receives an echo. On a rainy day, the signal bounces off both planes and water droplets. The system receives a club of points. It doesn't know for sure which points come from a real plane, the data we care about, and which are just atmospheric noise, the latent variable. We need a method that, from this chaotic cloud, is capable of inferring not only where the planes are, but also the parameters of their movement, such as the speed and direction, despite not knowing a priori which point belongs to what. This is the kind of problem that the EM algorithm solves with elegance.
The expectation maximization algorithm, or EM, is an iterative optimization method designed to estimate parameters in probabilistic models with relating variables. Its goal is to maximize likelihood when data calculation is interfered. To understand this, we will use a classic example: Gaussian mixtures. Imagine that we have data that appears to come from two different groups of Gaussian belts, but we don't know which group each point belongs to.
Let's formalize. We have a dataset X consisting of x sub 1, x sub 2, up to x sub n. We assume that each point x sub was generated by one of k Gaussian distributions. We introduce a latent variable c sub I that belongs to the set 1/3 k, which indicates which Gaussian generated x sub I. We don't observe c sub I. Our goal is to find the parameters theta, p sub k, mu sub k, and sigma sub k, for k from 1 to k, where p sub k equals the probability that c sub I equals k. It is the prior probability that a point belongs to component k, the mixture widths. Mu sub k is the main component k. Sigma sub k is the covariance matrix of component k. The probability density function of our data is a weighted sum. P of x given theta equals the sum over k of p sub k times n of x given mu sub k and sigma sub k, where n of x given mu sub k and sigma sub k is the probability density function of the normal distribution. We want to maximize the likelihood of our observed data. The likelihood function is the product of these probabilities for all points. But maximizing this directly is complex because of the sum inside the product and because we don't know the c sub I. This is where expectation maximization shines. The algorithm iterates in two steps. First, the I step or expectation step using the current values of the parameters, data subscript t. We calculate for each point x sub I and its component k, the positive probability that x sub I belongs to component k. This quantity is called gamma ik. It represents the responsibility that component k has for point x sub I. We write this as gamma ik equals p of c sub I equals k, given x sub I and data superscript t. In Gaussian mixture models, this probability is calculated as follows: gamma ik equals p sub k times n of x sub I, given mu sub k and sigma sub k, divided by the sum from j equals 1 to k of p sub j times n of x sub I, given mu sub j and sigma sub j. This formula, a direct application of Bayes' theorem, gives us a self-membership. Rather than assigning each point to a single value, we assign a probability to each component. In other words, given the current parameters, a point may belong to one Gaussian with higher probability and to another with lower probability. In simple terms, the algorithm asks how likely it is that this point was generated by each of the distributions. Next comes the M step, or maximization step, using the responsibilities gamma ik as weights. We recalculate the parameters in order to maximize the expected likelihood of the complete data, that is, the observed x and the latency. The new estimates are essentially weighted average. Updated weight. The new proportion of component k is the average of the responsibilities. We write p sub k equals 1 over n times the sum from I equals 1 to n of gamma ik. Updated mean. The new mean is the weighted average of all points, where the weights are the responsibilities. We write mu sub k equals the sum from I equals 1 to n of gamma ik times x sub I divided by the sum from I equals 1 to n of gamma ik. Updated covariance. This measures the dispersion of the data around each new mean. We write sigma sub k equals the sum from I equals 1 to n of gamma ik times x sub I minus mu sub k multiplied by x sub I minus mu sub k transpose divided by the sum from I equals 1 to n of gamma ik. Intuitively, each data point influences its Gaussian component in proportion to gamma ik, causing the distributions to shift and adjust their spread according to the data. This process is repeated. With the new data, we recalculate the responsibilities in a new step, and with those responsibilities, we update the parameters in a new M step. In other words, the algorithm alternates between estimating how much each component explains each point and updating the parameters of the model accordingly. With each iteration, the likelihood L of data given x increases. This continues until the chains become very small and the algorithm converges. At that point, the Gaussian components have adjusted to the structure of the data, and the model has reached a stable solution.
Carlos, it's time to see these formulas in action.
We start by creating a Gaussian mixture model with two components and feeding it to the eruption data using the fit function. We then assign each eruption to a group with dot predict function and calculate soft probabilities with dot predict probe. Predicted results show the number of eruptions in each group and simple assignments probabilities.
The Old Faithful Geyser is located in Yellowstone National Park in the United States. It is famous because it erupts with some regularity and tourists visit to see it. During the summer of 1995, scientists recorded 272 eruptions and noted two things for each one. How long did the eruption last? Minutes. How long did it take until the next eruption? Minutes. The interesting question is, are there typical short eruptions and typical long eruptions? And if so, can a computer figure it out on its own? This is the data recollected. Prior to the model implementation, an exploratory data analysis was conducted to provide the statistical justification for our methodology. The histograms for both eruption duration and waiting time exhibit a definitive bimodal distribution. This empirical evidence confirms that the dataset is not a single Gaussian population, but rather a mixture of two distinct underlying physical processes. Furthermore, the boxplot analysis and the discrete statistics reveal significant variance, particularly in the waiting intervals with a standard deviation of 13 minutes. The absence of extreme outliers is a critical finding. as it ensures the numerical stability of the EM algorithm and prevents bias during the iterative convergence process. Finally, the scatter plot demonstrates a strong positive correlation where data naturally segregates into two clusters. We emphasize this because the EM algorithm operates fundamentally on the estimation of means and variance. By confirming through the box plot and discrete statistics that there are no extreme outliers with duration range between 1.6 and 5.1 minutes and waiting time standard deviation of 13.59, we guarantee that the algorithm identifies the true underlying group of the geyser without being distracted by statistical noise.
Next, we visualize the clusters. Points are colored according to their group. Ellipses represent the Gaussian distributions, and stars marks the group centers. Annotations displays the means, duration, and weighting for each time cluster, giving a clear picture of separation and spread. We then print the parameters learned by the model. For each group, we display the width, mean duration, mean weighting, and standard deviations. This confirms that short eruptions last about 2 minutes with 55 minutes of waiting, and long eruptions last 4.5 minutes and 80 minutes of waiting. To examine improvement, we repeatedly feed the model with increasing iteration limits and record the total log likelihood. Plotting these values shows the curve rising and flaring, indicating convergence and illustrating how the M algorithm improves step by step. We test the models with different numbers of groups from 1 to 6 and calculate BIC and AIC scores. Printing a table and plotting the values shows that two groups have the lowest BIC, confirming this as the optimal number. We analyze assignment certainty by computing the maximum probability for each eruption. A scatter plot corresponds from green for high confidence to red for low, and a histogram shows the distribution of probabilities. Counting the points demonstrates that most eruptions are assigned with high confidence, while a few lie in the uncertain zone.
Mathematical and structural interpretation. The expectation maximization algorithm belongs to unsupervised learning, which means that it works with data without known labels. Instead, we use the maximum likelihood principle. The input for the algorithm is the set of observed data, all the points we have available. The output of the algorithm is the parameters of the probabilistic model. These values mathematically describe each cluster, its size, center, and dispersion. In addition, the algorithm calculates the probability of each point belonging to each cluster, allowing for flexible and probabilistic assignment. The objective function is to maximize the long likelihood of the observed data. The algorithm seeks to ensure that the clusters fit the points as closely as possible. The optimization criterion is as follows. Every time EM repeats the process, the clusters fit better, the explanation of the data improves, and the algorithm never worsens the model. It always improves it or keeps it stable. EM stops when the improvement is very small. It's no longer worth continuing to adjust. Important mathematical facts. The data follow a Gaussian distribution. Furthermore, each point was generated by a cluster we don't know. Given the component C sub I, the generation of X sub I is independent. Regarding limitations, the number of components K is a hyperparameter we must set a priori. If we choose poorly, the model will not fit well. It can get stuck in a solution that is not the best possible. For very complex models, the M step may not have a closed-form analytical solution.
Expectation maximization reminds us that even when information is incomplete, It is possible to build accurate models through rigorous statistical inference.
It's impressive how the EM algorithm is used in computational biology and medicine to analyze incomplete biological data, such as in the study of gene expression, DNA sequences, and medical image reconstruction. Its importance lies in its ability to train probabilistic models and uncover hidden patterns in complex data. Today we have journeyed from a practical problem to the equations that solve it. We have seen how iterative maximization of likelihood allows us to find a structure in datasets that seemingly lack organization. The EM algorithm teaches us a fundamental lesson. Sometimes, to understand reality, we must first imagine the possibilities and then let the data refine them. Thank you for joining us. See you next time.